Hi, welcome to Indefinite Integration Undoing the Derivative. So, as our first formal lesson with integration, we are going to look at this thing called indefinite integration. And what I'd like us to think about when we first start off in this lesson is we want to undo the derivative process. So, if you think back to how we learn derivatives, we first started with slope, so we attached meaning to the derivative with slope, and then we figured out how that process actually divided our y values and x values, and that became our derivative rules. And perhaps the easiest way to think about those derivative rules was with like the power rule or the chain rule, how we sort of dissected the pieces of those functions. Well, now we want to put things back together. We want to integrate, and we're going to do that by multiplying different things back into slope, or whatever our rate is, because that's what a slope is. So we'll eventually start to make more sense of the integral operation, and then finally assign more meaning to it. So you'll see this sort of get pulled out of our experiences here. But first we're going to start to work with it so we can eventually have those conversations. So our first example here is going to take 4 different functions. It's really just a cubic function that's been shifted different amounts. So you can see it right here. It's x cubed. It's been shifted up 1, down 4, and then up 2 pi. Remember, pi is not a variable, it's just a number. So that plus 2 pi is the highest the cubic has been shifted. But the result of a differentiation process is a derivative. So here, if we start off with functions like f of x, and then we take the derivative of them, then we'll end up in the same spot, because when we take the derivative of 1, negative 4, and positive 2 pi, that's all 0. So using the power rule, we get 3x squared for each and every one of them. The anti-differentiation process, so undoing the derivative or integrating, also known as the indefinite integral, that is going to get us back to where we were before. However, if we want to go back to one of these different functions, if we want to reverse the operation and go the other way, we can see that there are different constants that could produce the same derivative. So that's where this c comes into play. So this is an arbitrary constant. Which is why we can't exactly get back to the same function, not exactly, unless we have some other information, which will come into play later. So this arbitrary constant c is going to be part of our answer. So if we follow the chain of events here, we had f of x, and then we found the derivative, f prime of x, and then this brought us to what we'll call capital F of x, which is the integral of that result, and it's marked by plus c. So you can see how similar lowercase f of x and capital F of x are because of their format. Okay, great. So when we do this, when we do this process, so like how you learned how to take a derivative, there's a process for integration as well. But there is a symbol that we use for integration, and it's called the integral sign. It's written like a very flat, narrow S. So when I write it, I've got sort of a taller, narrow S written down. It does stand for sum. So it basically means sum. And you can see kind of what the integral is saying to do. It says sum, if you look over here on the top right, sum the y values times the different x values. So this is a multiplication process that we're doing. But again, we'll kind of explain more meaning as more of it sort of comes about these lessons. So, but for now, we have the s for the integral, and then this dx that explains what variable we're taking the integral with respect to, just like we did with a derivative. So it was like our dx or our dt when we were taking the derivative or the integral with respect to those variables. So when we apply the integral operation to any function, that s and that dx are going to follow each other around as the appropriate notation for our symbols. Now, because integration is, I think I need to do this. Yeah, there we go. I was the wrong way. Because integration is undoing a derivative, I decided to swap the rules and write it like this. So here's some basic integration formulas that you should be able to make some sense of. If we have any constant, like if it was a derivative rule, if we have any constant and we take the derivative of that, that's 0. If we have 0 and we integrate that, then we should get some arbitrary constant, which is why our answer here is C. If we take the derivative of k times x, then we know that's kx to the first. So we apply a little power rule logic to that, and we get kx to the 0, which is just k. So likewise, if we wanted to integrate that, if we start off with a constant, then we know we multiply in an x variable. And if we follow along the same line of thought, if we have a constant in our derivative, then we can move that constant to in front of the derivative operation and then take the derivative separately. Likewise, with an integral, if we have a constant in our integral, we can pull that out of the integral and integrate just f of x separately. If we have two different things inside a derivative, we don't have to take the derivative of that whole thing. We can take the derivative of each term separately. That works similarly for integrals. If we have different things inside our integral, we don't have to integrate it all at once. We can integrate it separately. And perhaps the most useful rules out of this, so if you've kind of zoned out the past couple seconds, perhaps the most useful rules are the power rules, because they kind of explain what's going on. We know the power rule with derivatives. We multiply into the constant of our term, and then we subtract 1 from that power. If we are going to reverse the power rule, then we are going to divide by the power n plus 1, and raise our variable to the power of n plus 1. So we'll see this in practice down below. So let's do a couple of these, and then the rest will be your practice. So I'm at 10 minutes right now. Hopefully we can keep it to 15. So let's look at number 4 here. Let's zoom in some. So that last rule, the reverse power rule, is going to be what we're primarily going to use. So if we want to undo the derivative here, we are going to use the integral rule that we can take the integral of x to the 4th separate from x squared. And not only that, but we can subtract the two integrals and have that negative sign outside the integrals as well. So if I'm integrating x to the 4th, then I'm going to add a power to 4. So instead of removing a power from it, I'm going to add a power to it, and then I'll divide by that power. So my answer is going to be x to the 5th divided by 5 minus add 1 to the power x cubed divide by that new power 3. And we want to make sure we put plus c there, because we know that there's an arbitrary constant that could create an indefinite set of integrals, which is why it's called indefinite integrals. So this is our final answer right here. Cool. I'm going to get rid of that box because it's covering up the 3 there. In fact, that doesn't look like a grade 3, so I'm going to rewrite it. Yeah, so that's the answer there. If we go over to another example, we have a constant in front of our variable, so we can rewrite this. Remember how much we love rewriting. We can rewrite this as 3x cubed dx, and then integrate just x cubed. So our answer is going to be 3 times whatever our integral of x cubed was. We've got a power of 4 because I added 1 to that power. And then if I divide by 4, it's the same as multiplying by 1/4. So this answer is also sufficient. And then it's plus c. And I'm just going to tidy this 3 times 1/4 up by writing it as 3/4. And that is our integral there. Do not forget your plus c. Okay, now 11 is not so bad. It's still using the reverse power rule. It's still going to use, like, you can separate these integrals. We can separate 2 over x cubed and 5 over x to the 4th as 2 separate integrals. But what we also need to do before we actually integrate is rewrite our variables as negative exponents, so we know how to integrate, because we don't like to see radicals like we see in some of these questions below, and we don't like to see powers in the denominator. So I'm going to write it as 2x to the negative 3 dx minus 5x to the negative 4th dx. And then I can integrate. So I can say negative 3 plus 1 is negative 2. So I've got 2 divided by negative 2x to the negative 2. And then minus 5 over negative 3 x to the negative 3, because I've added 1 to negative 4, so I get negative 3. So that'll be a plus because I'm multiplying, or yeah, a negative by a negative. So really what we're doing is a lot of multiplication, division, again, the simple operations that we've done our whole math lives. And I'm going to leave my answer like this because I've ran out of space, but what you typically do is make sure that exponent is positive again. Actually, I can just fix this real quick so you all can see it. Let's see, this was x squared, so that'll be in the denominator, and this was x cubed, and that'll be in the denominator. Cool. So the last one I wanted to do, and I wanted to warn you all about the last three, 16, 17, and 18. 16 and 17 are the ones I'm not going to do, but you want to rewrite them before you integrate. With 17, it's a little bit tricky to integrate because we've got to divide each term by x to the fourth. So what we're actually integrating is x to the negative 2, because x squared divided by x to the fourth is 1 over x squared, and that's x to the negative 2, plus 3x to the negative 3, and then plus x to the negative 4 dx. So by integrating these, we're going to end up with x to the negative 1 divided by negative 1 plus 3x to the negative 2 divided by negative 2 plus x to the negative 3 divided by negative 3. So I'm adding 1 to that power and dividing by that new power, and then plus c. And so it ended up being pretty easy if we could just divide each of those numerator terms by x to the fourth, which is what that operation is saying to do. And I'll just write this a little bit nicer for us. So 1 over negative 1 over x minus 3/2 with x squared in the denominator as well. And then minus 1 over 3x cubed plus c. So there you have it. That's the practice that you'll be doing. You'll be undoing the power rule essentially. And there are those other rules that are a little bit more nuanced in what we did before, but they're definitely in play here when we're undoing the derivative operation with the integral. So thanks for watching, and I'll see you guys later. Bye.